In this video, we're going to talk about phase transitions. So back early on in the beginning of the first semester of this course, we talk about changes of state and the names for those changes of state. So if you think back, going from a solid to a liquid is melting, and going in the opposite direction is freezing. So these two phase changes are opposites of each other. The same thing happens as going from a liquid to a gas. Going from a liquid to a gas is vaporization. Going in the opposite direction is condensation. So these two again are direct opposites of each other. And then finally we have going from a solid to a gas, or going back from a gas to a solid. These two again are exact opposites of each other. So we're going to talk about a little bit about what happens with these phase changes. So for example, if we look at the phase change between vaporization and condensation, between going from a liquid to a gas, or we sometimes use the term vapor for gas. So if we go from a liquid to a vapor, if we're in an open container, what's going to happen is that vapor is going to escape into the atmosphere. So this essentially becomes a one-way reaction, or a one-way phase change. Our liquid turns into our vapor, and then vapor escapes into the atmosphere. And as the liquid continues to turn into vapor, as we add enough energy for more of that liquid to turn into vapor, eventually all the liquid turns into vapor and escapes into the atmosphere. But if we're doing this in a closed container, there's always a little bit of vapor above the liquid if our container is not completely full. So what happens is, right at that interface between the liquid and the vapor, so this is our container here, and this is our liquid level. So we've got liquid all down here. So right at this interface between the liquid and the vapor, some of those liquid particles are going to have enough energy to escape into the vapor phase. But because this is in a closed container, what's going to happen is that some of those vapor particles, once some of the liquid turns into vapor, this increases the vapor pressure. But we're in a closed container, so we can't handle this increased vapor pressure. So some of those vapor particles are going to condense back down into liquid particles, and we're going to have some of those going into the liquid phase. So we get this kind of back and forth going on, where some of the liquid particles get enough energy to escape and become gas particles, and then some of the gas particles end up condensing back down into liquid to lower the vapor pressure. A similar thing happens with sublimation and deposition. If we have something subliming, so sublimation is going from a solid to a gas, or solid to a vapor. So if you're in an open container, you get a solid turning into a vapor, and because we're in an open container, that vapor can escape into the atmosphere. So this process just continues until all the solid has sublimed into vapor. If we're in a closed container, however, we have a similar situation to what we had with the liquid and the vapor. that we get this back and forth reaction going, where some of the solid is eventually going to get enough energy to escape into the vapor phase, and that would be the solid. There's some of that solid that's right at the surface between those interfaces between the solid and the vapor. Some of that, those solid particles right at the surface get just enough energy to escape up into the vapor phase, but then as we increase the vapor pressure, some of that's going to force that vapor to deposit back into the solid phase. One example of this is if you've ever had iodine. You've ever seen a particle of iodine in a solid container. What happens is if you put your piece of iodine, and iodine has like a violet color to it. It looks kind of blackish sometimes if you're just looking at a solid particle. But if you put your solid piece of iodine into the container, what eventually ends up happening is you'll start to see some violet color, and that violet color will get darker and darker until eventually it reaches a point where it doesn't get any darker. So what's happened when the container reaches a point where it's not getting any darker is that we've reached equilibrium. So the concentration of the vapor has become constant, and the concentration of the solid, or the concentration of the solid, has become constant as well. So we're still getting some of that solid turning into vapor and vapor turning back into solid, but it's happening at a constant rate, and it's going quickly enough in each direction that we essentially don't change the concentration over time. Now with melting and freezing, it's a slightly different story here. If we're in a closed container, the solid turns into liquid, and then some of that liquid that's right at the surface, on the surface of that solid, is going to adhere to the solid and essentially freeze again. But even if you're in an open container with a solid and a liquid, the liquid can't escape easily like the vapor can. With vapor, if we're in an open container, the vapor is just going to escape off into the atmosphere. But liquid doesn't have enough energy to do that. So it's going to stay right there at the surface. And if you don't pour that liquid off, some of it's eventually going to adhere to the solid surface and turn back into the frozen solid. So we're going to focus mainly on this top transition here, on vaporization and condensation, in the next few slides. And we're going to talk a little bit more about what happens here and the energy that's involved in that. So once we've reached a point of equilibrium, and let's stop for a second to find what equilibrium is. Equilibrium is the point where the change going back and forth, the rate of liquid to vapor and vapor going back to liquid, is happening at the same pace, at the same rate. So essentially the concentration of liquid and the concentration of vapor does not change over time, because we're going from liquid to vapor at the same speed that we're going from vapor to liquid. So if we're going back and forth at the same speed, then the concentration, if you calculated the concentration, you would find that you get the same answer each time, because we're going fast enough in each direction that we end up creating just as much vapor as we do liquid. when we go back and forth in these phase changes. So once we've reached a point of equilibrium where these reactions are going in both directions at the same rate, and we're no longer changing the overall concentration, once we've reached that point, the number of molecules in the gas phase is not changing. So because of that, the pressure that's exerted over the vapor, that's exerted by the vapor, remains constant. So if you think about it, you put your liquid into your container, and if we've just put the liquid in there, then some of those liquid particles are going to start to escape and form vapor, and they're going to continue to do that. So for a while, the concentration of our liquid and our vapor is going to be changing. And then eventually, we reach that point of equilibrium where we have these liquid particles turning into vapor, but we've also got some of those vapor particles turning back into liquid. So this is where we've reached equilibrium. And if we were to calculate concentrations, we'd find that the concentration of the vapor and the concentration of the liquid remains the same over time. So once we've reached equilibrium, the pressure of a vapor over a liquid is referred to as vapor pressure at that point. But we have to be in equilibrium to truly refer to it as vapor pressure. The vapor pressure of a liquid will always increase as we increase temperature. As we increase temperature, we're adding more energy, which means more of those liquid particles are going to become vapor particles, and more of them will stay in the vapor phase. So we will have to reestablish equilibrium. But once we've reestablished equilibrium, we will have more particles in the vapor phase at the higher temperature than we did at the lower temperature. So because we've got more particles, we're going to increase the vapor pressure. If you increase the vapor pressure high enough that you equal the atmospheric pressure, that's the point at which the gas particles have enough energy that they can escape and they can go off into the atmosphere. So once we've reached that point, we call that the boiling point. The normal boiling point is defined as the temperature at which liquid will boil at 1 atm. So if you are at a different atmospheric pressure, if you're above sea level or if you're below sea level, you'll find that the boiling point is slightly different because you have a slightly different atmospheric pressure. That's why you'll find sometimes at higher elevations that you have to cook at slightly different temperatures because your normal boiling point, the temperature at which water boils is slightly different because you have less atmospheric pressure. So the point at which the vapor pressure equals atmospheric pressure is going to be a lot lower. So sometimes you have to adjust cooking times and cooking directions because of that. In chemistry, we define the normal boiling point as the point where liquid boils when the pressure above the liquid is 1 atm. So anything else is not at the normal boiling point. So there's actually an equation we can relate pressures and temperatures and the pressure at which a vapor will boil using the Clausius-Clapeyron equation. So the Clausius-Clapeyron equation tells us if we take the natural log of the new pressure over the old pressure, that's equal to the delta H of vaporization, so the enthalpy of vaporization, or sometimes we refer to this as the heat of vaporization, over R, which is our gas constant, is equal to 1 over the original temperature minus 1 over the new temperature. So you need two different pressures and you need two different temperatures to do the Clausius-Clapeyron equation. So you have to measure the pressure at two different temperatures in order to calculate the heat of vaporization or the enthalpy of vaporization. Those two terms mean the same thing. And you will sometimes hear this referred to as the heat of vaporization, sometimes you'll hear it referred to as the enthalpy of vaporization. So we will actually get some practice working on the Clausius-Clapeyron equation in class and see how we can use that and plug some values in and calculate delta H of vaporization for different temperatures and pressures, or calculate what pressure would be given the pressure and temperature for another value. So we'll get some practice with that equation in class. So as we're going from one phase to another, it takes a certain amount of energy just to change phases. So for example, if we start with a solid and we get up to the amount of energy where we can go from a solid to a liquid, there's a certain point where all of that energy is going into turning that solid into a liquid. So at this point, if you were to measure the temperature of the liquid that's there, what you would find is the liquid is at 0 degrees Celsius, because we haven't added enough heat to increase the temperature. So we continue adding just enough energy to the solid to turn all of it into the liquid phase. And then once we've got everything in the liquid phase, we can add more energy to increase the temperature of the liquid. Now once we get to a point where we're between the liquid and vapor phase, we're now at the boiling point. Now all of our energy is going into turning this liquid into a vapor. So if you could theoretically measure the temperature of the vapor, what you would find is it's still at 100 degrees Celsius, because we haven't added enough energy to start increasing the temperature of that vapor. And then as we continue to increase the temperature, then we would, or as we continue to add energy, we would add energy and increase the temperature of the vapor. Now we can also represent phase changes using a phase diagram. And a phase diagram gives us slightly different information about the phase changes. So if you take a look at a phase diagram, what we have on the far left is the area where our substance is a solid. In the middle here is where our substance is a liquid, and over to the right is where our substance is a gas. So there's a point at which the temperature and pressure are right for this substance to be a solid. So at high enough pressures and low enough temperatures, our substance is going to be a solid. At low enough pressures and high enough temperatures, our substance is going to be a gas, and therefore somewhere in the middle of that, we're going to be a liquid. So you can see where the line is between these phase changes. We go from solid to liquid, which is melting, going back across that line will be freezing, and so forth for all the other phase changes. But there are 2 points on a phase diagram that are particularly of interest. One of them is this point between all 3 phases that we call the triple point. So the triple point is the temperature and pressure where all 3 phases of a substance coexist. So if you're exactly at the temperature and pressure for the triple point, you will have some of your substance in the solid phase, some of it in the liquid phase, and some of it in the gas phase. And all 3 of these phases coexist at this point. The other point that's of interest is the critical point. So the critical point is the specific temperature and pressure where both the liquid and the gas phase have the same density. So typically a liquid would be more dense than a gas. But at the critical point, we get to just the right pressure and temperature, so that the liquid and the gas actually end up having the same density. We can actually make a phase diagram for pretty much any substance, and that phase diagram gives us some specific information about the substance. For example, if we look at the phase diagram for water, we can see where the triple point for water is and where the critical point for water is. So if we look at this diagram, the triple point for water is at 0.01 degrees Celsius and 0.6 kilopascals. So at this temperature and this pressure, we have ice, liquid water, and water vapor. That all exist all at the same time, even if we had these in the same container. So these coexist at that point. And if we make just very small incremental changes to the pressure or the temperature, we could change all the water that we have at this point into a solid or into liquid or into a gas, just by making those very tiny changes in pressure or temperature, because that triple point only exists at this very specific point. Now this point is going to be different for different substances. The specific pressure and temperature will be different for different substances. But whatever the specific pressure and temperature is for the triple point for that substance, if you change the pressure or the temperature just slightly, then what you will do is force all the substance into the solid or the liquid or the gas state, because now you are no longer at the exact pressure and temperature needed for those three phases to coexist. So we're going to stop here, and we will get some more practice with some of this in class. And I will see you in class.